Okay, hi everyone. Today in this lab we're going to specifically do three different things. The first thing is we're going to learn how to set up an intrusion detection system. After that, we're going to learn how to convert the intrusion detection system into an intrusion prevention system, and in the process we're going to also learn how to perform a denial of service attack. The victim virtual machine, or the virtual machine where we will set up the intrusion detection system, will be our Ubuntu operating system. And like with any virtual machine, before we get started, the first thing we want to do is run a basic set of commands that would update and upgrade the virtual machine. Now, once we're all set up, we will move ahead with installation of Suricata. This is going to be our intrusion detection system for today, right? So Suricata is a very popular tool. It's open source, and it's fairly easy to install. I've already have this installed in this virtual machine, so I don't have to take you through the installation process, but regardless, this is a very easy installation and you shouldn't have any problem setting this up, right? So now that we have already installed our intrusion detection system, let's set it up to perform detection activities before we attack this virtual machine, right? So the first thing we're going to do is Suricata comes with its own configuration file in YAML format, so we're going to be editing that. We're going to use nano to edit the configuration file, and it sits at etc/suricata/suricata.yaml. Okay, within the configuration file, these are the three most important things, and these are the three specific things that we will be doing today for the intrusion detection part, right? So first thing we want to do is identify the IP address. This is very important, not just knowing the IP address, but also knowing the interface. You will get to know soon enough why that matters, but we're just going to IPNA. We will see that, okay, the interface is right here and the IP address is right here. Here under HomeNet, this is where we need to specify the address groups. What we need to do is specify this exact IP range for where the virtual machine is sitting, just to make sure that the detection is being performed specifically where our virtual machine is, or accessible to the network interface. So this would be basically the first thing that you want to do. The second thing we want to do is Control F and try to identify where AF packet sits. This is how Suricata enables a monitoring mode within a virtual machine. Essentially, this makes sure that we set the interface that we want to monitor, and essentially the service calls upon the AF packet module to start the monitoring activity. In the interface, this is what's important. We need to specify the exact interface that we'll be monitoring. In this case, it's ENP0S1. So we're going to write that there. So that's the second thing we needed to do. The last thing we need to do is this isn't like super important. We could actually just write inside of suricata.rules, but a couple of things I wanted to show you. So the rule files sits in this particular directory, or you can specify your own directory. That's up to you. But for this purposes, the lab purposes, we're just going to copy this particular file directory, which we're going to use later on, and we're going to also show you that you can actually have any file that you want. let's say local.rules instead of suricata.rules, which currently local.rules does not exist, but we're going to create one. So that's all. That's all you needed to do within the configuration file. And once you're done, you can just exit this. And another thing we need to do now, a very important one, is actually set up the rules, right? And then we got local.rules. So this was the file path we previously copied, but for some reason it wasn't copying it into this terminal. I'm just going to press enter so that we open this file up. This is where we write the rules, which we will use in order to perform detection activities or raise alerts. So we're going to start with alert, ICMP, any to any, that would be going to home net, which is where we specify the IP address, if you remember that. That happened just a second ago. And then we're going to broadcast a message. The message is going to be, let's say, alert ICMP flood seems to be happening. Detected more than 5 packets within 5 seconds, right? So this is just a message. So we need to actually write the rule that would send out this alert every time this actually happens, right? So threshold, we're going to have set type as limit, which means when it hits the limit, it's going to raise one alert. I'm sorry. Yeah, one alert. And then we have track method, which we're going to use by source, which is the source IP address. And then the count will be set to 5 as we specified in the message. And then we're going to say seconds will be 5 as well. So last thing we need to do is a signature ID. You can have this as anything you want, to be honest. Right. So we're going to be writing another rule, okay, just to make sure that we have some kind of redundancy, or multiple rules, just to make sure when we're describing the rules, I'll be in a better position to explain you how all of this works. So we're going to write in another ICMP rule, which essentially, well, most of the thing is actually the same thing as above, but in the message we're going to have something different, right? So in this one, I'm gonna have critical ICMP flood seems to be very aggressive. If that was the right spelling, I'm not sure, but it doesn't matter. Okay, so we're going to close it at this. Oh, maybe not. We need to specify what is our expectation towards it. So let's say exceeded 20 packets in under 2 seconds. Let's keep it 2 seconds or 3 seconds. Okay. And what we're going to do is, yeah, we're just going to write out the rest of the rule here. Threshold type limit source count will be 20 this time, because we were looking for more than 20 packets within 3 seconds, right? And SID would be just something that's different from the previous one. That's all we need to make sure, right? So that's it. We've written 2 rules that are going to be used by Suricata to detect and alert us upon. Now, we did a lot of typing, and we need to make sure what exactly happened with the rules. Are they syntactically correct? The first thing you can do here, and this is very common practice, is that you can actually perform a test on the configuration file to make sure everything is loading up correctly before you actually start spinning the service. So command for that would be exactly this: Suricata YAML. That's the configuration file. We initially made those 3 changes, if you remember that one. And once we press enter, yes, clearly you can see that there seems to be a couple of errors here with one of the rules. So we go back to the rules and we see that there isn't a $sign before we wrote the home net, so it wasn't able to identify what that was. Maybe with this change, yeah, now it's working. So that's it. This is how you check a configuration file is syntactically correct or not. Make sure that you perform this before we move on and starting the service up. Let's restart Suricata, and I'm going to check its status. All right, so this is what we were looking for. It's running, it's active, and we now officially have an intrusion detection system ready and listening for any traffic that would generate alerts based on the rules that we specified before. Right, that's great. Now we need to be monitoring the log files, which is very important. There are multiple log files that Suricata enables generating. You can also configure and specify that within the YAML configuration file that we worked on earlier. But for the purposes of the lab, it's not important for us to tweak around and play with the existing configuration. We're just going to be using fast.log. If you've used Snort before, this is also a log file that is commonly used by Snort for generating logs and alerts. What we're going to do is use a command called sudo tail, which follows a file that is the log file we're going to be working with right now. Suricata says fast.log. So when we type this, when we enter this command, we're basically, the terminal will be listening to any changes that happens over fast.log. Make sure that the logs are going to be written directly into the terminal, so we can see the alerts being raised right here. Great. So we will now move on to performing a denial of service attack. So this would be the second part of the 3 parts that I specified at the introduction of this lab. As a student, it's very important for you to consider that these commands, and I'm going to clear this up, these commands could be malicious in nature. So if you don't specify the count or the time limit, the speed of sending of the packets, it is likely possible that you will be crashing the victim machine. And personally, having done this multiple times, it's not a great experience having to restart virtual machines again and again. So I would suggest that you exactly follow the commands that I've specified here and perform these actions against either your own virtual machine or the virtual machine provided by the course instructor, specifically for the purposes of performing this lab activity. Okay, that was my disclaimer. I'm going to move on to describing what the command is trying to say. The sudo hping3 is hping3 is the tool that we're going to be using. -1 specifies we're going to be calling an ICMP attack, and -I basically sets the speed of sending the packets. I believe if you have 250,000, that's 0.25 seconds. So if we have 2500, that's pretty fast. I don't know the exact numbers. We can probably Google that up and get to find out how fast U2500 is, but I'm pretty sure you'll see this when we send the attack to the victim machine. It's going to be pretty fast. So the count is number of packets that we're going to send, and in this case I'm going to send 100 packets over IP address 192.168.64.3, which is the victim, the Ubuntu virtual machine where we set up the intrusion detection system, right? So I'm going to press enter here, and I'm going to type the password for it. the operating system. As you can see, the 100 packets were like, I don't think it took even 1 second to send everything. So we're gonna check and go back to the Ubuntu, and you can clearly see we already have logs generated. You can see the first log that happens is an alert. The first rule that we specified, flood seems to be happening. So it detected more than 5 packets within 5 seconds. This is what we were hoping for. So it would, grab the first 5 packets, exceed that, and then trigger the first rule. After that, we have another alert called critical. ICMP flood seems to be very aggressive, exceeded 20 packets under 3 seconds. So again, another rule that we needed to specify, it happened. But why did it not, why did it not raise so many different other rules? Because we sent about 100 packets, right? Here's the thing. So before we get to that, I'm going to explain you the remaining 2 packets. With ICMP requests, what happens is that you send a request and you receive a response from that virtual machine back to your machine where you send the flood attack from. So in this case, if you look at the IP addresses, 64.2 is Kali Linux and 64.3 is Ubuntu virtual machine. So the first 2 alerts raised seem to be sending packets from point 2 to point 3, so Kali to Ubuntu. But from the third packet, we have 3 to 2. So we actually replied, because this is not an intrusion prevention system, it's just sitting there and listening to all the traffic that's going in and outside of this virtual machine. So it just raised an alert that saying that there was a Ubuntu virtual machine sending out 2 ICMP replies back to Kali Linux, or not 2, more than 5 within 5 seconds, right? And the second one, again, very similar to how we had the second alert for Kali Linux to Ubuntu. It's doing exactly the opposite. So under 3 seconds, we send out more than 20 reply packets. But why not have raise alerts for more than that? Well, the first rule detects any activity within 5 seconds and then waits for 5 seconds before it can detect another one. Since the attack in itself did not even exceed a second, it happened within that 1 second. It only generated that one alert. And that goes the same for the 20 packets under 3 seconds, because if the 100 packets took maybe 5 seconds, then you would have 2 of these alerts probably. But in this case, since everything happened under a second, probably from Kali Linux, we only have 1 raised alert. That's it. Well, basically what you did was you detected an attack incoming into your virtual machine and successfully raised an alert and are able to read and understand what the alert is trying to say. This was the second part of the lab, and now we're going to move to the final part of the lab, which is setting up your intrusion detection system into an intrusion prevention system, right? How we're going to do this, again, we have to go back to the configuration file where we did all the magic, I would say. And first thing we have to identify AF packet. Now, an interesting thing about AF packet is that it does monitor your system, so it's a very good, capture support, like it says there, for monitoring. But when it comes to sitting in line and trying to, drop or reject the packets, it doesn't have the feature functionality to do it. So what we're going to do here is that we're going to hash out or comment out all these configurations, just to make sure that they are not there within the configuration file anymore. And we're going to replace that with something else. So the alternative of AF packet would be setting off an NFQUEUE, which enables the Suricata to sit in line, which means it will be sitting in the middle of Kali Linux and this virtual machine. Well, technically not in the middle, but in the forefront of whatever Ubuntu is receiving or sending out, but it will be able to perform those actionable items such as dropping the packets, which we're looking to do in this set of the lab. Okay, so this is it. This enabling NFQ with these configuration would essentially allow us to do exactly what I specified before, convert our intrusion detection system into an intrusion prevention system. So we're going to exit the configuration file. Maybe might as well test it once just to see if it's working. You can see here that it's setting engine mode to IDS by default. Still, it's going to do that. It's understandable because Suricata.service actually has AF packet calling under the configuration file. So I'm going to show that where it is. Systemctl status Suricata. You can see here that it's calling out the AF packet. So when I restart this and it's not able to do that, it will crash itself, unfortunately, but we're not going to allow that. So what we're going to do is that we are going to make changes. That would be edit Suricata.service. We're going to make changes here, right? Sorry. Okay, so what we are looking for is we are trying to change this into NFQ mode, and for that we need to do -Q0 enables the NFQ mode, and essentially what it does is that, well, I can, once I restart it with the rule changes and linking the NFQ rules into the iptables, which is a very important step that I need to do, it will be able to be, make those actionable changes. What we now need to do is we need to make changes in the rules that we already have. It's very important that we have a drop rule so that we can perform something actionable within the Suricata when we do send out another set of traffic. And for that, we're going to use a drop command or drop rule, ICMP any to any, and we're going to send out this to home net any with message that says ICMP dropped, and then we're going to say something like rate had exceeded from 3 packets under let's say 3 seconds, right? Okay, so that's the description of the rule, and then we're going to type 8 for ping requests and detection filter. We're gonna have track by destination, and another thing we're going to do is set the count as 3 seconds, which would be the time as 3, and then move on to having a signature ID would be, as for this, any random number is it's fine. Revision 1. So that's it. We have officially written a rule that would prevent any ICMP requests. Okay, yeah. So any ICMP requests from the attacker box that would exceed more than 3 packets under 3 seconds. We're going to write out this file, we're going to exit this, and we're going to perform the test to make sure that the rule, here you can see 1 signature processed and 1 rule file processed and 1 rules. So that's that successfully means that we have the rules available, and we can now move ahead with doing a couple of things on iptables. Now, another important thing is, well, if you don't know what an iptables is, it's basically an open source firewall tool that is, you know, given out of the box in most of the Linux distributions, right? So what we're going to do here is that we're going to have iptables input NFQUEUE. So we're going to insert NFQUEUE in here, and that's going to basically allow Suricata to, you know, or NFQUEUE to actually perform actionable activities using the rules that is available with it. We're going to do the same thing for output. There's another thing, you know, if the virtual machine or the Suricata service is running as a proxy, we can specify that forward and make sure that it can block traffics that are intended to be sent to another device or target. Okay, this pretty much completes our work that we need to do, but we're going to verify this by listing out the iptable rules, and you can see all the rules are implemented here. We have NFQUEUE in all three input, forward, and output chains. This is what we are looking for, and the only thing that's left now is to perform daemon reload, and then we're going to perform restart Suricata. Before we even restart it, I'm just going to show you status, and here you can see it still says AF packet. We did make changes to the suricata.service, if you remember that. However, we're not going to bother with that here right now, and once we do restart this, that's going to change. Takes a bit of time, but once we go back to the status, it's active and running. That's a good thing, and it's now converted to NFQUEUE mode. So it's is now able to do what we have been looking to make it do from the first place, right? So we're going to be listening in to the same fast.log which had the previous logs. And another thing we're going to do here, just to show you or explain you better how this works, we're going to install Wireshark. Oh, sorry, we're going to run Wireshark. But if it's not there, of course, we have to install Wireshark. So Wireshark is another open source tool that can perform, well, it acts as a packet capture for the network interface it's sitting on top of. So it captures all network activities once you assign it to an interface. That's all it does, but then it gives us a very visible insight to whatever is happening within that network or the network device. A lot of different use cases around Wireshark. As you can see here, all you get to do is select one of the interfaces and run the start. Enables the scan, and you're able to start capturing any network packets that come in and out of this interface. So we're going to start both the Wireshark and keep the fast.log tail open on terminal. What we're going to do now is we're going to perform the same attack, but we're hoping that this time is gonna react. The virtual machine, the target virtual machine, is going to react differently. Something interesting happened. The first 3 packets were sent. Then 97% packet loss, which means out of 100, 97 of them weren't received back, so those were dropped. And this is what we are looking for. And we can clearly see here. I'm not going to take you through the whole logs or count the number of times this log appeared, because it's probably 97 times the logs appeared saying that ICMP dropped rate exceeded from 3 packets under 3 seconds. So we're going to take a look at this, and we're going to select the source and the destination IP address to make sure that we are seeing all the requests we were looking for. So you can see here that there were about 100 displayed, and only 3 got a reply, whereas the others found no responses. We can verify that through switching the source and the destination IP addresses as well. You can see that there were 3 replies that were sent, echo reply were sent, but after that Suricata managed to drop all the packets that were incoming towards this virtual machine, ensuring that it does not spend a lot of resource trying to reply to all the 100 ping requests, or even more in case of denial of service, an actual denial of service, or at a very large scale when it comes to distributed denial of service. Well, this is what we were looking for. So the third objective of this lab has been completed. Thank you for going through all the videos, and thank you for following the steps that are provided here. You have successfully managed to learn how to implement a intrusion detection system, perform a denial of service attack, and block the denial of service attack by converting an intrusion detection system into an intrusion prevention system. That's it. Thank you.